Okay, so I'll make a couple announcements at the end, but there is a faculty meeting tonight. Depending on how long the vote goes on the stats major, I will be there sometime between 5:30 and 6:30 admission for the weekly review. I will send an email to the class just updating the status. Okay. What I want to do today is discuss analytic continuation. We'll then talk about some common sequences. We'll shift to number theory, and we'll see some issues. And then that will hopefully motivate the physics that we're going to then do for a while. So, analytic continuation. And so the idea is you take a function which is given by, is it still recording?
Yep.
Okay. You take a function that's still recording, I just keep hearing these beeps. You take a function that is given by a series in one region where you understand it, and you try to figure out how would that function be defined in another region. So the standard example is the geometric series. And so for the geometric series, 1 plus r squared equals what?
Are we going off to infinity?
We are, of course, going off to infinity and beyond.
Okay, well, 1 over
1 over 1 minus r if the absolute value of r is less than 1. And if we want to think of this more complex analytically, we would replace 1 with z. Be 1 over 1 minus z if the absolute value of z is less than 1. So what's nice is there's a very obvious candidate for the extension of the sum of 1 plus z squared plus z cubed for all values of z except for one point. What's the obvious extension? 1 over 1 minus z. Right? That's the obvious candidate. So we define 1 over 1 minus z as the analytic, or maybe here meromorphic, continuation of 1 plus z squared plus dot dot dot. And so what this means is the two functions agree where they're both defined. But this makes sense for other values of z. And in fact, it makes sense for all values of z but z equals 1. Yes?
Is this especially useful because we have mappings from the disk to the entire complex plane?
Okay, say that again.
So it seems that since we can map the entire complex plane to the disk, and this is only
Wait. When we map the entire complex plane to the disk, we can't do that one-to-one onto.
Okay. Never mind.
Okay. So, one of the biggest questions in analytic continuation is the analytic continuation unique? Is there more than one way to continue something? And so if you think about the logarithm, we initially have the logarithm defined on the real line, and then we've come up with an extension. We can't define it all the way. But we do have two different ways to define, or actually have infinitely many different ways to define the logarithm. So what I can do for the logarithm, I start off where here's the real line, and we understand things on the real line. What's a good place to choose for our branch cut? I use the red again.
The negative
The
real.
negative reals. And so if I do that for my branch cut, if I want to figure out what's going on down here, if I take z equals minus I, that's going to be e to the negative I times 3 pi over 2. The log of minus I would equal what? Negative 3 pi over 2 times I. And if we have that as our cut, that is how we would continue the logarithm function. But there's other ways we could have done it. I could have chosen that as my branch cut. And if I chose that as my branch cut, it's not, I'm sorry, it's not e to the negative I 3 pi over 2. What is it? E to the negative pi over 2. Because we're going down 90 degrees of pi half radians. So if I do it this way, I travel around 3 pi over 2. And so again, the problem is there's multiple ways of writing I, or multiple ways of writing minus I. And so now we write minus I as e to the 3 pi I over 2. And so now the log of minus I is 3 pi over 2 times I. Alright, these two are not equal. One way to resolve this is to say, well, I shouldn't really be using the same symbol for both of these. They're different continuations of the logarithm on the real line. And maybe what I want to do is I want to have some kind of subscript that will tell me how I've chosen my slit, how I've chosen. So maybe I call this region omega 1, maybe I call this region omega 2, and we can put on subscripts like that. But what this tells you, unfortunately, is that logarithms can be continued differently, or more generally, if I give you a function, it is not a unique analytic continuation. So then what question do you want to ask?
What conditions do we need to make it unique?
Excellent, that's a great question. What conditions do we need for the analytic continuation to be unique? There's another question you can ask.
What kinds of functions have unique analytic continuations?
That seems essentially,
It seems like-
Pat's just, rephrased.
Maybe.
Yeah. I don't know, what do you think, Pat?
It's with an M&M. Well, okay.
Okay, wait, but who? Who gets the M&M? Alright, so one question asked twice now is which functions or which conditions will give us uniqueness?
Very different words.
Very good, yes. And Williams is a liberal arts college, and of course we do encourage all of these skills to be developed. But there's a second question that is fundamentally different. That is not just a rephrasing, yes.
How many continuations?
How many continuations? Right? Or related to how many, but slightly different, so I can get an M&M too, is how different can the analytic continuations be? So if they're not the same, how much do they differ by? Now in this case, the difference is very interesting. What is the difference between the two? 2 pi. It differs by a constant. So if I give you 2 analytic continuations, do they always differ by a constant? So I'm not going to go into too much detail. My philosophy in teaching advanced classes like this is to really work you guys to the bone in the first part of the semester. And yes?
I had more of a question related to that. Are there going to be more different ways, more continuation of log minus I?
Yes.
But
Although you'll only get one of these 2 values, I think.
right, so there's only 2.
So for this case, there's only 2 for this one, yes. For this one, these are the only 2. So then an interesting question becomes, can you give me a function which has 3 distinct analytic continuations? Okay, so that's a nice extra credit problem. So my philosophy in classes, and if you disagree, just let me know, is to work you guys really hard in the beginning of the semester, and then towards the end of the semester when some of your other professors might realize they haven't assigned you enough work and they're not going to quite hit the end of the course where they want to be and they increase the workload, I go in the other direction. I kind of back off a little bit on homework problems and whatnot, and I want to just give you a little bit of a flavor of what's out there. A lot of you are going very different careers from Williams. I want you to get a sense of what's out there. I do not feel the need to overwhelm you with homework and problems like that. If you want to, I'm happy to give you additional supplemental ones, but I want you to just get a sense of what are the topics, what are the issues, what can you use complex analysis for. And so a lot of what I'm going to do over the next month is give you a little bit of a flavor of things. So the rigor is going to go down a little bit because I want to cover a bit more material. So things I definitely want to cover is analytic continuation, Riemann-Zeta function, quantum mechanics, Fourier series, and several complex variables. Right? One complex variable is very different than one real variable. What do you think happens with several complex variables? So, it's an interesting thing as to how would things change there. And again, if anybody wants to do a project, which can count as 10% of your grade, and you want to present something to the class, let me know. Okay. So what I want to do now is I want to turn to the Riemann-Zeta function. So zeta of s is the sum, n goes from 1 to infinity, 1 over n to the s is the product over p prime 1 minus p to the minus s inverse. And I'm just writing p to the minus s to save space at the top of the blackboard. Where does this sum make sense?
Real part of S is greater than 1.
Good. So real part of s is greater than 1. So as long as real part of s is greater than 1, this makes sense. So the question is, can I come up with a definition of the zeta function that agrees with this when the real part of s is greater than 1, but makes sense for other values of s? So I'm going to show you two approaches. One of them I'm going to just sketch, and I'm not going to go into full detail. And then the other one I'm going to go into full detail. And we will see that both of them are insufficient for our needs. And that will motivate a beautiful theorem called Poisson summation, or the Poisson summation formula. And to prove the Poisson summation formula, we'll need to then do some Fourier analysis for maybe 1 or 2 weeks. And once we've done all that Fourier analysis, it's just a few minutes to do the incident principle in quantum mechanics. So since we're in the neighborhood, why not just do that then? Right? So the motivation will either be number theory, streaming video, in terms of that's a great application of Fourier series, or quantum mechanics. So the issue with this sum is that we could have convergence problems if s is equal to 1 or smaller. And again, if s equals 1, you have the harmonic series. If s is a real number less than 1, it's even worse. Does anybody know a cousin of the harmonic series that converges?
The alternating.
The alternating harmonic series, right? The alternating harmonic series converges. So we're going to define zeta star of s to be the sum, and it goes from 1 to infinity, of -1, I think it's n plus 1 over n to the s. Now, I sadly can't remember if it's n plus 1 or n. Does it really matter? I'm sorry? Or n. Why does it not really matter?
It still alternates.
It still alternates. This is going to just change by a minus n. Do you want to start it at 1 over n to the s? Do you want to do it as 1 over 1 minus 1 over 2 to the s? Or do you want to start off with -1 over 1? Just -1 over 1 just seems bad to me. So we'll see in a few moments which one is the right definition. Right now I actually kind of prefer leaving it a little bit vague like this, because the idea is to move from the zeta function to the alternating zeta function, which has better convergence properties. So if the real part of, if s is a real number, the alternating zeta function converges. So converges if s is real and s is greater than 0. And that's just because it's an alternating series with one additional fact. What's the additional fact that I need to get convergence? So s is real, s is greater than 0, it's alternating. Why do I have that the series converges?
Because the absolute value is decreasing.
Because the absolute values are decreasing, right? So because the absolute values are decreasing, it has to converge. So the question now is, how can I get from the zeta function to this function?
You have to apply a -1 to the end.
Can I do that? So I can't just shove a -1 to the, I would lose my chalk for doing something like that. I can't just put in a -1. But let's think. They look a lot alike. So when you have things that are like, there's a couple things you can do to them. You could add them, you could subtract them. Which would you rather do? Would you rather add or subtract?
Do both.
Do both, right? Do both and see which one works better. So no, when you don't know what to do, you either split it or find a complementary friend, and then just see which way the algebra is going to work better. Okay? Let's look at zeta of s and zeta star of s. And so now this is going to make a difference as to how we choose to do it. We choose to do it with an n plus 1 or an n. So if we do it with an n, we start off with a 1 over n to the s. And so what I'm going to do is I'm going to make a non-random choice and put in a minus sign. What do we get when we subtract?
Are we starting with n plus 1 or n?
So we're going to do n.
Okay.
I'm sorry, n plus 1. We're going to do n plus 1.
You get double all the even terms.
You get double all the even terms. And so if I had done it with an addition, what would I get? So double all the odd terms.
Oh,
Yeah.
Which would you rather have, double all evens or double all odds? Given that I said it's not a random choice, which would you rather have? Double all evens. Alright, so why do I want double all evens?
Because then you can put in complex numbers and they'll become real numbers when you square the odds. Or you can put in purely imaginary numbers.
No, so let's write what we have. So we'll have 2, the sum of m even, negative 1.
Wait.
I'm going to write m. Sorry. We don't have the negatives anymore.
Yeah.
So m is even. We have 1 over m to the s. So how can you write an even number? So this is the same as 2 times the sum, n goes from 1 to infinity, 1 over 2n to the s. Now I think you can begin to see why I like the double all evens rather than double all odds. What algebraic simplification can I do to that sum? Yeah, I can pull out a 2 to the s. And so I get zeta of s minus zeta star of s is I have 2 divided by 2 to the s. So I have 2 to the 1 minus s. And what am I left with? I'm left with?
1 over n to the n.
Exact same thing.
And the sum of 1 over n to the s is just?
Zeta.
It's just zeta of s. This is the bring it over method, right? I have what I want to study on both sides of the equation. And as long as this coefficient is not 1, I win. If this coefficient is 1, I get zeta s minus zeta star of s equals zeta of s. So the only difficulty is if this coefficient is 1. What would I need for this to be 1?
S to be 1.
Okay, if s equals 1, I have the sum of 1 over n that blows up. Okay, I'm really not expecting to get much information at the point s equals 1. Any other point, however, I'm getting some facts. So I get zeta of s minus 2 to the 1 minus s is zeta star of s. Or, in other words, zeta of s is 1 minus 2 to the 1 minus s inverse zeta star of s.
You left a zeta out of the left-hand equation.
Yeah.
The left-hand side.
Oh, yes, we did, thank you. So, that's one way to cover myself, thank you. So zeta of s is 1 minus 2 to the 1 minus s inverse zeta star of s. That one was too close to the parentheses. Or another way of writing this is zeta star of s is 1 minus 1 over 2 to the s minus 1 zeta of s. So you give me zeta of s, I give you zeta star of s, or vice versa. Zeta star of s makes sense for any s that's real, but that's greater than 0. This allows me to now define the zeta function at other values. I can, in fact, figure out what zeta of 1/2 is. Okay, and zeta of 1/2 is a fun number. Okay, I can use this. Now the question, of course, is can I evaluate the series expansion for zeta star of 1/2? I know it converges, but I'm going to be something like 1 over square roots. Okay, so just because I have a formula for it doesn't necessarily mean I can extract something useful. But this does give me a continuation of the zeta function to s greater than 0. And in fact, you can show this works as well if s is complex. The key fact is that there's nice cancellation. I'm going to just do real part of s greater than 0. There's a lot of incorrect proofs of the Riemann hypothesis that use the zeta star function. It's still useful. It gives me an analytic continuation. It gives it cheaply. I wanted to write it both ways because there's a nice interpretation for what I'm doing here. And if you think about it, I'm essentially removing the 2 factor from what's going on. So I really don't want to talk about this in too much detail, but if you think about the product, if you take the prime and your p equals 2, that's kind of related to what I have here. I have it with a -1 here, I have it to a first power here. There's some connection between what's going on. So again, there's a limit to how deeply I want to go into things. I want to just put a couple of things on your radar screen. Yes?
This still isn't defined at s equals 1, right?
It is still not defined at s equals 1. Now if we try to define it at s equals 1, let's see. What is zeta star of 1?
Alternating harmonics.
It's the alternating harmonic series. What's the alternating harmonic series?
Converge. Let me read that out.
So, do people want to see what zeta of 1 is from this?
Curious.
It's been a long time since I've done this, because the convergence here is terrible. But it's a good thing to ask. Let's see what it is. Fortunately, I recognize a friend. Zeta star of 1 is 1 minus a half plus a third minus a fourth. Does anybody recognize that? The log of what? It is the log of 2. The log of 1 plus x is x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. If I put in x equals 1, well, I have some issues, but fortunately everything does work. I can take the limit as x rises to 1. This is the log of 2. Zeta star of 1, or zeta star of s, converges to the log of 2 as s goes to 1 from above. Or do I want to go from below? No, I want to go from above so I have convergence. Alright, so zeta star of 1 is well behaved. What about 1 minus 2 to the 1 minus s inverse? As s goes to 1, what do we get there? You get 1 over 0. Okay? It's actually going to work out beautifully. Alright? So let's study 1 minus 2 to the 1 minus s inverse. Okay? This is the same as 1 minus e to the 1 minus s log of 2. Right? Because 2 is e to the log of 2. I get 1 minus, now when I expand this, the first term in the exponential is 1. The next term is going to be 1 minus s log 2 plus 1 minus s squared log squared of 2 over 2 factorial plus dot dot dot. And I have to take the inverse of this whole thing. When I look at this, the 1's cancel, and I get 1 minus s log 2 plus 1 minus s squared. So when s is really close to 1, the denominator looks like 1 minus s log 2. This is where blackboard space would be really nice. But, all right, I'm going to leave the relationships for zeta and zeta star. And this is a nice way to review calculating residues, and just to see exactly how far can we push this method. So 1 minus 2 to the 1 minus s inverse is 1 over 1 minus s times the log of 2 times 1 plus 1 minus s log 2 over 2 factorial plus dot dot dot.
Isn't this the sphere of 1 minus that one?
I'm sorry?
Oh no, the whole thing is it.
Oh, and I have a negative sign from this as well. Thank you. So now, if I want to see what does this look like as s goes to 1, well, I can basically expand this out. essentially all that it really is this is really close, this looks like 1 minus s times the log of 2. Right? So if you expand it out, you get negative 1 over 1 minus s log 2, and then when you expand this out, 1 plus blah. Now, the zeta star of s, what did zeta star of s go to? So 1 minus 2 to the 1 minus s inverse zeta star of s goes to the log of 2 with a negative sign over 1 minus s log 2, which is just 1 over s minus 1. And if you've seen anything with the Riemann zeta function, if you've seen its analytic continuation, that's exactly what you get. The Riemann zeta function has a pole of residue 1 at 1. It's a simple pole, it's a pole of degree 1. So you can actually extract that out from the alternating zeta function. And the key fact is that we can interpret zeta star of 1. We know what that value is. And then we have this issue over here. And so we just have to be a little bit careful with the Taylor expansion of that, but we're able to extract the pole of the zeta function, which I think is really nice. So the behavior of the zeta function, it blows up, but we now know how it blows up at s equals 1. It's blowing up like 1 over s minus 1. Okay. So excellent question. If you go on to graduate school in math, you typically have to take general exams in real analysis, which includes measure theory, complex analysis, and algebra, which includes Galois theory. And then often schools will give you 1 or 2 additional topics depending on what you're interested in. And at the time, you know all the material cold. And then years later, I remember learning that so long ago. What was the... So these analytic calculations, I find them fun. But there's much more powerful methods than this. And so what I want to do now is I want to do another continuation of the zeta function. And there's several different ways. I don't quite like the way that's in the book. And so I'm going to just do a slightly different one. So if you've taken a class with me before, you'll remember the method of divine inspiration. And so I feel it's appropriate for me to be holding the piece of paper, which has come down from mathematician. And I'm going to look at s over s minus 1 minus s times the integral from 1 to infinity of bracket x dx over x to the s plus 1. And here, bracket x is x minus the floor of x. It's the fractional part.
I've seen that before.
The floor or this?
I've not seen that before.
Extra.
So, there's several ways we could do the calculation here. I'm choosing to just start with the answer and work backwards. You know, too many times we've gone in the other direction. Let's just be divinely inspired for once in the interest of time. But let's just see, is this at least reasonable?
Can I put that on my homework? I was
You can.
inspired divinely by
You
the
can.
interest of time.
You can. In one of my homeworks for differential equations, we were told to invoke, Theorem 3.2, and I actually wrote a paragraph invocation. And so, why is this a natural thing to look at? Well, the zeta function, we call, zeta of s is the sum, and it goes from 1 to infinity of 1 over n to the s. Does this kind of look like that? Yeah, kind of. I mean, I've got a 1 over x to the s plus 1. If I integrate 1 over x to the s plus 1, what do I get? Thank you for this.
X to the S.
I get 1 over x to the s, but what do I have to divide by?
That's-
So if I integrate,
Oh, then there's the.
I divide by negative s,
yeah.
right? So if I integrate this, the x to the negative s plus 1 goes to x to the negative s over negative s. Oh, the negative s cancels the negative s over there. And so if I didn't have this, that would be giving me maybe something like this. Now I've got to basically play little games, and so the idea is that this should look roughly like the 1 over n to the s. that the fractional part of x is not changing too much. Well, it's not so easy to deal with, the fractional part. So what I'm going to do is I'm going to replace the fractional part with x minus the integer part. And I'm going to break this integral up. I'm going to break it up from 1 to 2, and 2 to 3, and 3 to 4, and 4 to 5. Because in those ranges, the floor will be constant. And so now if we study things, okay, the camera's already been moved. So we have s over s minus 1 minus s times the sum, and it goes from 1 to infinity, the integral from n to n plus 1. And now the fractional part of x becomes x minus n divided by x to the s plus 1 dx. So how should I do the integral? Yeah, split it up. So we get s over s minus 1 minus s times the sum, and it goes from 1 to infinity. And then the first one, n to n plus 1, I have x over x to the s plus 1. So that's going to be x to the negative s dx. And then I subtract n times the integral from n to n plus 1 of x to the negative s plus 1 dx. Okay. Can I combine all of these integrals and make it go from 0 to infinity? Or 1 to infinity? So can I say, look, I've got a sum of the integral here, can I just combine this up and it goes from 1 to infinity? And then I combine this over here, right?
I'm worried about the second one.
I'm sorry?
I'm worried about the second one.
I'm worried about the second one.
Okay, I'm worried about all of them actually. Why is this dangerous? Is the sum of a difference the difference of the sums? Like in calculus we had, the derivative of a sum is the sum of the derivatives, the derivative of a difference is the difference of the derivatives. Is the sum of a difference the difference of the two sums? Or is there a condition that you often forget to check?
There's probably conditions.
There's probably a condition. Yes. Yes. What is that condition?
It's uniform convergence. I just guess. It's always that one. It's gone.
Gone. At least one of the two expressions must be finite. We can't deal with infinity minus infinity. So if both of these were infinite, we could have trouble. So we have to be very careful. I can't execute the sum yet. So I have s over s minus 1 minus s, the sum, and it goes from 1 to infinity. Now let's look and see what we get. If I integrate x to the minus s, what do I get when I integrate? Okay, so I get x minus s plus 1 over, I evaluated at n and n plus 1, and now I subtract n times, and now when I evaluate this, I get x to the negative s over negative s at n and n plus 1. Have I made any mistakes? Okay. Does that look good? No mistakes so far? Alright, so s over s minus 1 minus s, the sum, and it goes from 1 to infinity. Now let's look and see what we have. When I have n plus 1, I have 1 over negative s plus 1, 1 over n to the s minus 1 minus 1 over n plus 1 to the s minus 1, 1 over n to the s minus 1.
What the s minus ones?
I'm sorry? I'm sorry?
Aren't the s minus ones negative s plus ones?
Right, but I'm putting them in the denominator now. And now over here, minus n, and now I have when x is n plus 1, I'll have 1 over n plus 1 to the s minus 1 over n to the s, and I have a negative s over here. Okay. Is this beginning to look?
Are we subtracting in there? The first pair of brackets?
Yes. So is this beginning to look useful?
There's a minus sign in the bracket somewhere, right?
The first pair of
In
brackets.
the first bracket.
The first part? Oh, yes, yes. There's a minus sign between these two things like this.
I mean,
Do you see anything that looks like the zeta function, the sum of 1 over n to the s?
There's
there's a couple of
There's a couple of them. And so I'm going to leave it here and let you finish it, okay?
Wait, what the? You said you had two different methods of analytic continuation. This is the second one, right?
This is the second one.
The one you said you were going to go in very detail.
Yes. This is. All you have to do is simplify the algebra. This is 372! Simplify this and find zeta of s. Come on!
Oh, no, I would just check.
Yeah.
I would just check. Oh, that's fine.
I mean, what's algebra here? Algebra is what? 350, what did we rename it? 355? We're above that.
I don't know what we call it.
It's not a prerequisite.
It's not a prerequisite. It's not even a prerequisite to be the instructor for this course. At this point, it's algebra, okay? I want you to do the algebra. Or I will, give you a handout that, completes the algebra here. Can you see 1 over n to the s coming into play?
Sure.
And this n over here, if I bring the n down below, n to the s minus 1, that's going to be the same as this over here. Things I'm going to have s's and s plus 1s are going to cancel, and I'll get a 1 over there. So you can begin to see the algebra coming. And if I want to work with maybe this term, I can write n as n plus 1 minus 1, play games like that. So it's a good exercise for you to do something like this. Okay? I am not going to do that. Again, this is the advantage of just trying to give you a sense of the topics. I have hopefully brought this to a point where you can see things will happen, but not go into all the details. Let's look at what we have again. This is the same as s over s minus 1. And if I want, I can write s over s minus 1 as s minus 1 plus 1. So if I write s as s minus 1 plus 1, I get 1 over s minus 1. So I'm writing s as s minus 1 plus, I've just written s as s minus 1 plus 1. Oh, 1 plus s minus 1. The reason is that's going to cancel with the s minus 1 over here. So write s as 1 plus s minus 1. 1 over s minus 1 plus s minus 1 over s minus 1 is 1. Plus the integral,
Oh, there's the one. Okay.
yep, from 1 to infinity of the fractional part of x dx over x to the s plus 1. And so I wanted to say a few. I'm sorry? Oh, there's a minus s, I think, in front of this. So I wanted to say a few words about this. The first is, notice, there's the pole, 1 over s minus 1. The second is, when does this integral converge? For what values of s does that integral converge?
S positive?
S, you can be a little bit better than s positive.
S greater than negative 1.
No. No, but s positive is on the right track.
No,
But you're being too provincial. What class is this?
Oh, right. S greater than absolute value. Greater than, or real part of S.
The real part of s greater than 1, right? So this is okay if the real part of s is greater than 1. Oh, sorry, greater than 0. Greater than 1. As long as the real part of s is positive, as long as it's greater than 0, I've got x to a power a little bit greater than 1. And that's integrable because I'm going from 1 to infinity. I don't have any danger of behavior near 0. I only have what's going on as x gets very, very large. And because the power of x in the denominator is greater than 1, it's integrable at infinity. Do I have to worry about the fractional part of x? No. How large can that be? At most 1. So this is a really nice continuation of the Riemann zeta function. It gives you a formula for the Riemann zeta function for any s greater than any s whose real part is greater than 0. Okay? Alright. Any questions on this so far? So what I want to do now is I want to sketch a proof of the prime number theorem and see why these analytic continuations are not enough. And we're going to need a better analytic continuation. And that better analytic continuation is going to require Poisson summation. And that's going to be why we're going to start the tour into Fourier analysis. And then as long as we're there, we might as well prove some convergence theorems, might as well prove a bunch of things, and might as well end up in quantum. Okay? So let's look at the prime number theorem. So pi of x is the number of primes p less than equal to x. So I can write that as the sum of p less than equal to x of 1. One of the things I love about being in the math department is I am allowed to discriminate. Now, I have to be very careful as to college-sanctioned ways to discriminate. Baseball affiliation is acceptable. I have checked with the college. I am allowed to discriminate based on what team you root for. That was the first email I sent after getting tenure. Sorry? Yeah, absolutely. Another way I can discriminate is I don't have to treat all primes the same. I can treat some primes and give them a greater weight than others. And instead of studying this, it's actually better to put these slowly varying weights on the primes. So again, if you think about it, it often takes a while for limiting behavior to set in. And so with the log p weights, the stuff that comes later is weighted a little bit more than the stuff in the beginning. But the weights do not vary that wildly. And so the question is, why do we care about something like this? So we haven't done too much with this yet. This is called the Euler product. And if it wasn't for the Euler product, we would not care about the Riemann zeta function. It wouldn't be of use to number theorists. But because of the Euler product, we have a relation between sums over integers and sums over primes. I want to extract information from this. So what I'm going to do is I'm going to show you how we can do that. And we'll go back into a little bit of results about Weierstrass and factorizations. So some of the stuff we did early in the semester will kick in again. But before, what's the first step I should do in the analysis? So I've got the Euler product. What's the first thing I should do?
Take logs.
Take logs. Log of zeta of s is negative sum over p 1 minus p to the minus s. With the log. If I take the log, I have to take the log. Okay. What is your favorite quantity to integrate in complex analysis? That's not trivial.
Derivative over
The primitive, you want to integrate f prime over f. How could I get a zeta prime over zeta?
Take the derivative of both sides.
Yeah, what's the derivative of log of zeta? It's zeta prime of s over zeta of s. This is called the logarithmic derivative. So whenever you have a function in complex analysis, you want to integrate f prime over f. Take the logarithmic derivative. And if you happen to be fortunate enough to have a product expansion, life is great. Right? Because the log of a product is the sum of the logs. And now I just have to take the derivative of this. So I have minus the sum over p. Alright, the log, so I get a 1 minus p to the minus s down below. And now I have to take the derivative of negative p to the minus s. The negative of the negatives will become positive, and I'll get p to the minus s times the derivative of p to the minus s. I'm sorry. P to the minus s is e to the negative s log p. So I get a log p when I come out. Okay, so the exponential is e to the negative s log p. I get itself back, and then the derivative of the exponent is just negative log p. Now I use the geometric series formula to expand out the denominator. and I will get negative sum over p to the minus s log p plus the sum over p to the minus 2s log p plus double dot. And I'm just expanding out the bottom. So p to the minus 2s is going to have much better convergence properties than p to the minus s. What do I need s to be for this to converge? Real part has to be greater than a half. Here I need things to be real part greater than 1. I'm not going to worry about these other terms. Of course, if you're proving the prime number theorem, you have to worry about all of them. But I'm going to say, let's just ignore all of these, and let's just study the sum of p to the minus s log p. Okay? So all we'd have to do is just do some bookkeeping on the remainder. We've almost got the proof of the prime number theorem. It'll be close. So we have zeta prime of s over zeta of s, leave a little space, is negative sum over p of log p times p to the minus s. Okay? So I want to take an integral of both. So I'll be somewhat vague as to where I'm integrating. And now I need to choose what to integrate it against. I could integrate it just against itself, but it turns out technically it's very nice to multiply by x to the s minus 1 dx. Or do I want to do x to the s? Which way do the more transform? No, I want to do x to the s. Okay. So again, there's also plus something that's nice. Okay. And now, let's say I integrate over the real part of s is 1 plus epsilon. So if the real part of s is 1 plus epsilon, we write s as sigma plus it. Sigma would be 1 plus epsilon. T would go from minus infinity to infinity. Right? And I've just integrated both sides. It turns out you can show that this piece is small. I have an integral here, x to the s, p to the minus s. That integral, amazingly, turns out to be 1 if p is less than x, and 0 if p is greater than x. It's a beautiful integral. So we'll talk more about this integral later. This integral gives me a sum over p less than or equal to x log of p. And now you can see why number theorists like to discriminate, or at least one of the ways we like to discriminate. We like to discriminate with a log p way to the primes because when we take the logarithmic derivative of the Riemann zeta function, a log p comes out. This is why we don't treat primes equally. This is the quantity that's easy to study. And then there are techniques that's called partial summation. It's a discrete version of integration by parts that allows me to pass from knowing the sum of log p to the sum of 1. Over here, if you think about what we're doing, now here's the universe. Here's 0, here's 1, here's 1/2, here's 1 plus epsilon. We're integrating along this line. In complex analysis, what would you like to do? I'm sorry?
On a closed contour.
You want a closed contour. So what you do is you go up to height t, down to height minus t, and you close it off. And now, the integral over the closed contour is basically just going to be the residue at the zeros and the poles. You then have to show that the contribution on the bottom and on the far left is negligible in the limit. And then all I have to do is just look at the residues. So this is why I need to analytically continue the Riemann zeta function more than just to the real part of s greater than 0. I need to be able to push this line off to minus infinity so that the contribution over this side is negligible. And I need to then figure out where are the zeros of the Riemann zeta function. Well, I have a pole of the Riemann zeta function at s equals 1. We've already seen that. So the contribution, oh wait a minute, I should have something over here. What should I be multiplying by? 1 over 2 pi r, right? And so now, when I get a pole of the Riemann zeta function, the contribution from a pole is plus 1 or minus 1?
Plus 1.
I'm sorry? Minus 1. So the pole gives me an x. Because we know the Riemann zeta function has a pole at s equals 1. And now we have minus a sum over all zeros of basically x to the rho over rho. Oh, sorry, so the integral I need is, I actually have to divide by s if I want the integral to be the harmonic detector. So I get the following. And so we'll talk a little bit more about this formula and why this implies the prime number theorem. Basically, I said the number of primes up to x is like x over log x. This gives me the weighted sum of the primes is of size x, as long as all the zeros are less than 1 for their real part. Well, if I've increased all of my numbers by the log of p is approximately log of x for all these primes. So the number of primes should really be about x over log x. We'll go through this in more detail. But what I wanted to just get to today is you've seen the formula, you've seen the punchline of where we're going to go and how we're going to get the prime number theorem. You can see the complex analysis coming into play, and you can see that we need more than just a continuation to the real part of s greater than 0. We need a continuation all the way to minus infinity. And so I'm going to have to develop Poisson summation. That's the way I know to get the continuation. So that's going to be the motivation. So starting on Friday, we will then do Fourier analysis. So we're going to go